Let's get started here. We'll start by talking about electric dipole physics. Dipoles, of course, play a very important role in physics and chemistry and engineering and so on. A lot of materials have dipoles in them, or these dipoles are created by applying electric fields. So if you take a number of gases, liquids, and solids, if you let them interact with electric fields, have these dipoles that are created, and materials which are insulated and form these dipoles are called dielectrics. So what is a dipole? Well, it consists of two equal and opposite charges. So over here we have minus q and plus q, separated by a distance d. We treat these dipoles in two ways. One is d is small, and the other is that we actually take the limit of this system as d approaches 0. That's an ideal dipole. For most purposes you can just take d small and treat it like two charges. So the dipole moment is centered at the point P, and so we have these same two charges in the point P, and a vector little p, shown here, centered at the point P, represents the dipole, and it points from the negative charge to the positive charge. So the direction of P is from minus to plus. That's very important to remember. The unit vector that points along that same direction we call p hat, and the magnitude of the vector p is equal to q times d. So in other words, the vector p is equal to q times d times the unit vector p. So let's take a look at the potential due to a dipole. And so what we have here is a system where we have the 2-point charges, we have the vector d, which represents the distance between these two charges and in the direction of the dipole. If we take this point P and circle it around the z-axis, which is the orientation direction of the dipole, you'll notice that it really doesn't matter about the value of the potential here, because these positions are all equivalent. So this really has to do with the symmetry of the problem. There's symmetry about the z-axis. So what that means is that there's no phi dependence. So we can basically ignore that. Let's look at how we get that potential. The spherical coordinates, we've already said that will be simply dependent on r and theta, and this will be independent of phi. R and theta define the point P relative to the center of the dipole, which is here at the position O. Looking at what that potential is, we say that it's the sum of the potential due to plus charge plus the sum due to the minus charge. And from our Coulomb treatment of charge, we know that the potential due to the q is equal to this quantity, and due to the minus q is equal to this quantity, where the distances from the charge to the point P are r plus and r minus. And so that's these distances right here. Now they're approximately equal to r, but they're slightly different. If we take this expression here and multiply both top and bottom by this quantity right here, then what we get is kq times r minus minus r plus over this quantity here. Okay, so now we make an approximation, and we say if r is much greater than d, then the difference between these two vectors will be equal approximately to d times the cosine of theta. And so what we're talking about really is this distance here, because if you take a perpendicular between this quantity here and this is the right angle here, then you've got a triangle here, and the cosine of theta times d will give you this length here. And so that's the difference in length between those two vectors. The other approximation is that if we take r minus times r plus, since these are close to the length of r, one being shorter, one being longer, we'll just simply set that product equal to r squared. Putting this approximation and this approximation into V, we then get the expression for the potential at the point P right here as a function of r, which is the position vector of the point P, the length of that vector, and the angle theta. That's the angle between r and the z-axis. Okay, so if we identify that q times d is the magnitude of the vector P, then we can write the potential, as we show here, as k times p cosine theta over r squared. A very simple equation, but one that's very useful. we consider this distance d to be very small. This expression up here was exact. We didn't make any approximations. This expression here is only for our condition for the approximation to be valid. Let's take a plot of V in the plane of this drawing here. So we're staying in this plane, and we're simply drawing the value of the potential from that expression earlier as a function of the distance from the dipole. So we put a minus charge here and a plus charge here. Then we take the expression that we had and plot that, and what we find as we approach the dipole, we have the positive charge causing this to go on infinity at this position. The negative charge makes it go to negative infinity at this position, and you're just seeing what's left over on these curves here. As you go to plus or minus infinity, this goes to 0. It goes to infinity at the positions of the charge. Another way of plotting that is basically a 3D plot. In order to do this plot in Mathematica, I have to change it to Cartesian coordinates. This is the z-axis down the center of this plot, and the x-axis is in this direction here. So again, we have the same situation. Here's our minus, here's our plus, and we're looking at the infinities in the potential now as a function of both x and z. You see again the nature of this potential going to infinity. So right here is where the charge is. So the plus charge is right about here, and the minus charge is right about here. What you're seeing is the truncated version of this. So this goes way up and then comes back down again. And then you see how it falls as a function of the position, and you see how it falls in both x and z. Here's v along the z-axis, and this is the 2D or 3D plot, whichever you want to call it, where this quantity in this direction is the actual potential, and the position is given by z and x. So because of the 1 over r squared dependence of this potential, v falls off relatively fast with distance, and so you get down to pretty small values fairly quickly. What about the electric field? So we have the same charge distribution and distance and so on, same vectors. The way we find the E field is to take the potential, to find the E via the negative of the gradient. The gradient is going to be taken in spherical coordinates. Realize that we can take our potential, P is a constant, K is a constant, so we can bring those outside of the operator delta. Here's our minus sign. So then we just have the gradient of cosine theta over r squared. So you've got to look that up. The gradient in spherical coordinates is the partial of the function with respect to r times r hat, and then 1 over r times the partial of the function with respect to theta hat. There's another term in phi, but we don't have to worry about that, so we just cross that out. So doing that, and you end up with kp over r cubed, notice the cubed, 2 cosine theta r hat plus sine theta, theta hat. Notice that the negative signs become positive signs. I've shown here a plot of the streamlines because you get a better picture of how the E field flows, so to speak. But notice that all the arrows are going from plus charge to minus charge. If we looked inside the dipole, this is what it would look like. If you go outside the dipole, you see these very large fans of E field that go from the plus charge to the minus charge. Also shown are these circular-like lines, and those are the contours of the potential. So as you go towards the negative charge, these circles become colored darker and darker, and what that means is it's going negative. You're going to negative values of the potential. Over here it's getting lighter in color, and what that corresponds to is that the potential is increasing. It's the same thing that you have here, where the contours are cuts at constant values of potential. As you go to higher and higher values, you get these curves as a contour across this function here. And the same thing goes over here. So you'd have a cut across here giving you one of these curves, the contour curves. So that is the field and the potential of a dipole, which is a useful set of equations.
Well, there's a very useful equation that's given right here for the electric field of a dipole. And this is in a problem that's commonly assigned. Show that for a point given by the position vector r, E sub r for a dipole at the origin, oriented along the z-axis, is given by this expression here. So here's the problem. We orient the dipole along the z-axis. Here's our position vector for the E field determination. Here's our unit vector along that vector. The angle between P and R is the angle theta, which, because of the way we oriented P, is the polar angle theta. So when we display the dipole moment P, which is this red arrow here, we've already said that this is the angle theta, so that if we wanted to find the component of P along R, that would just simply be P times the cosine of theta. That would be P dotted into R hat. So now to determine P theta, it's convenient to rotate the coordinate system right here around the z-axis. So the vector r is in the plane of the paper. So both P and R are in the plane. Theta hat is in the direction of increasing theta. So I've shown this little vector here as theta hat. And it's normal to the r vector. So if we look at the angles, what we have between P and theta hat is the angle theta to here, and then another pi over 2 here. So we can write down then that phi, which is the angle between those two vectors, is equal to theta plus pi over 2. Well, we know that if we take the dot product of P with theta hat, that'll give us P theta. So that's given by P times cosine of phi. So then we just put this expression right here, and so we have P cosine theta plus pi over 2. So expanding the cosine, we get minus sine of theta. So P theta is minus P sine of theta. And so putting that together with P sub r, P cosine theta, we get the expression for P in terms of P sub r, P sub theta. So P cosine theta, r hat, minus P sine theta, theta hat.
Alright, so now let's try to crank out this expression here. So we've already commented on P sub r being P cosine theta, but that's exactly equal to P dot r hat. So we're starting to get something that might be included here. Let's go back to the old expression for the E field from the dipole. And remember, here's our 2. We had P outside, but now we put it inside the brackets. And so otherwise it's identical to what we've used already. So here's the little trick. We say 2 cosine theta is 3 cosine theta minus cosine theta. This is exactly the same thing that we have here. And so now we expand that in terms of the E field. We put the 3 here, and here's the minus. Those two terms are in the direction of r hat. But then we still have the theta dependence here. Here's our 3 term. Here's the combination of these two terms. And if I put a minus sign out, then there's a minus sign here. This is where we recognize this quantity here as equal to the dipole moment itself. And we've already said that P cosine theta is equal to P dot r hat. So you put all this together, and what you have is the expression that we want, k over r cubed, and then 3 P dot r hat minus P. So that's our so-called famous equation. One thing I want to emphasize, now we have a quantity that depends on 1 over r cubed. So the magnitude of the electric field falls off very fast with r. Another important application of dipoles is how they behave if you have them in an electric field. So here we show a dipole with a uniform electric field E. And so here's our field, and you can see the parallel lines heading in the z direction, say. The dipole moment, remember, is in this direction here. We want to find the torque due to this dipole put into the field. And so we first identify the forces. So there's a force on the positive end, which is just Q times E. The force on the bottom end is minus Q sub E because of the minus Q. So those are the forces. Realize that these charges are in the plane of the paper and it's uniform E field, and the total force, because these are equal and opposite, is equal to 0. We already can say that if we put a dipole into an E field that's uniform, the total force is equal to 0. So it's not going to be pushed back and forth. But now let's look at the torque in terms of the distance vectors from the origin. You may recall that the torque due to a force on a set of objects is given by a cross product between the vector connecting the rotational axis to the mass, or to this object, crossed into the force. The two terms then are basically R plus cross F plus and R minus cross F minus. So the magnitude of the force is equal to, okay, now let's look at this. It's d over 2 times the unit vector in the plus direction. D over 2 is just this distance here. The minus term looks exactly the same, except we have R minus here. Realize that those are pointing in opposite directions. Realize that both these terms are into the paper. So that's the right-hand rule. You curl your right hand between R and the F, and that'll give you the direction of the torque. We factor out a d over 2. We put those outside, and then take the force and introduce that. The cross product introduces the sines of the angle phi. And this phi is the angle between the orientation of the dipole and the E field. Okay, so that's phi. There's a factor of sine phi in both of these, and so when we add those two together, we keep that sine of phi, and notice we've got Q times D times E sine of phi. QD is equal to P, and so we end up with T equaling P times E sine of phi. So if we revert back to vector notation, the vector tau is equal to P cross E. So again, we have an interesting and useful equation for a property of dipoles in electric fields, namely they want to twist. Okay, so look at where this wants to go. If the forces are like this, then when this dipole, let me draw it here, when the dipole orients along here, and in this case the plus end here and the minus end here, that's the lowest potential energy state. That's where it wants to go. So the torque on this system is equal to 0. If you now go 90 degrees like this, then sine of phi is equal to 1, and so you have the maximum torque on the dipole. If you wanted to, you could take the dipole, take it to almost 90 degrees and let go. And what will happen is the dipole will oscillate back and forth. And because we haven't put any damping into this equation, it'll just keep going. It's like a harmonic oscillator, a torsional harmonic oscillator. One more time, the direction of this torque, again using the right-hand rule, taking P into E, your thumb will point into the paper. So let's find the work done by the electric field on the dipole as we rotate it. So what do? Well, we start with the torque that we just derived, and we use the equation that's analogous to the linear work. So a little bit of work is F times dx. Likewise, if we have a small change in phi, the work done is the torque times d phi. So putting in our torque in terms of angle, then we end up with this expression for the work. We'll worry about the sign later in terms of who's working on what. So we integrate that from any starting angle phi 0 to a final angle phi, and that gives us the magnitude of the work done in rotating P into E from phi 0 to phi. So here it is. It's the work is P sub E times the integral of sine phi from phi 0 to phi phi. Doing that integral, we end up with this expression here, where we have phi here and phi 0 here. This is an important equation, but we're not done yet. If we take the same equation that we just derived and look at this in terms of the work, one thing you want to realize is that the work done by the electric field is minus the work done by us. That is, if you were pulling or pushing the dipole, that would be you. Again, for us, in quotes, to rotate the dipole from a small phi sub 0 to a larger phi, we have to do positive work. And that goes back to what I was saying before in terms of the torque. So in other words, if you started here and you went here, you would do positive work to get that dipole to align. If we look at the above equation, for phi going from a small phi 0 to a large phi, the work that's given here is minus. Why? Because what we're doing is we're going from a small phi, which is going to give you a large value for cosine phi, to a large phi, which is going to give you a small value. So that's what gives us this minus sign. So we rewrite that in terms of the work done by E. So we've now decided that this is what E does. This is PE cosine phi minus PE cosine phi 0. But now we want to find the potential as a function of the angle. So we look at the way work and potential are related, and it's basically this, that if we have a change in the potential energy with a minus sign, that's going to be the work done. So if we define the change in U as just those two U's evaluated at those two angles, then if you take the negative, of course, you'll get this right here. We therefore identify U as minus PE cosine phi. That's equal to minus the dot product of P with E. So the potential energy of a dipole in an electric field is equal to minus P dot E, which of course is related to the cosine of phi. Let's go back to how we found this. This was looking at how the work done by the E field determines the potential energy. If we wanted to do the same calculation where we do the work, then we would find that we get exactly the same answer. So in other words, this is a system quantity that does not depend on who does the work and will be the potential energy of the dipole. So what does this look like? Well, if you take this function here with a minus sign, realize that this will be crude, but if you take the value of cosine and just forget about PE, the maximum value occurs at 0. This is phi. The maximum of cosine phi is at 0. With the minus sign, we're down here. Okay, so what does it do as you change phi? Well, you know that. It goes to 0, like this, like that. This is the minimum value. When this is lined up, when the dipole is lined up, you're at a minimum. Well, that's basically a potential well. If you start at some phi, like this, you start here at one of these values here, it'll oscillate back and forth like this, so that when it's down here it has maximum kinetic energy of torsion, and here it has 0. And so the torsional pendulum will oscillate back and forth from these two values. So we've found then a expression for the work done and the change in potential energy of the dipole in the field, and they're given by simple results. Okay, now this is more subtle. This is looking at what is the force on an electric dipole in an inhomogeneous electric field. We've already shown that in a homogeneous E field the force was 0. In an inhomogeneous E field, the force on a dipole in general will not be 0. So consider a dipole in an electric field that has a gradient, and I've just put the gradient along the axis of the dipole, but it can be in any direction. If you look at these streamlines as representing the E field direction and so on, if you have high density of field lines, you have a strong field, and as it goes to less dense distribution, you have a weaker field. So remember, this is the direction of the field at any point. We go back to finding the total force again, and we've already said it was the difference between the plus and the minus forces, and so I've drawn those here. And because we're in the weaker field here, this is shorter than this right here. And so that is the origin of the force on the dipole. If we take the difference between the two forces, factor out the Q, then we have Q times delta E, where that's the change in the field from this position to this position. If we look at it again, here's the same diagram, same force. If we now take a look at this in terms of x, so this is the x direction, so if this is the x direction, this would be the total force acting on it. And we realize that this quantity here is over a distance d, which is very small. So if we have this small, we can represent it as follows. We can take the difference in field and relate it to the gradient of the field, and actually the gradient of the E sub x term. If we dot that into d, that will give us the x component of the change in the field. Well, there are similar formulas for the change in E sub y and E sub z, where our orientation not as aligned as this one up here. So we can write the vector delta E, that's the change in the field now in 3 dimensions, as the gradient of E dotted into d. And if you remember, you can rewrite that as d dot del, where this is the del operator acting on E. And I think you remember that you take dx dot partial with respect to x plus dy partial with respect to y, and so similar for z. That's how you actually do this, and then you operate on the components of E. We've done this before. So we can now write for the force on the dipole P given by this right here. But look, here's Q times the vector D. That's the vector P. And so for the force on the dipole that's in an inhomogeneous electric field, it will be given by this quantity here. If you realize then that there is a constant E, then that's going to give you 0, which is what we had before. If this has a change with position, then the operator del will give you a non-zero value for the force.